Hello everyone. So in this video series, I am going to discuss about the subject thermal engineering, fuels and combustions. The topic fuel types in the mechanical engineering. So this is the presentation overview I am going to discuss in this session. So fuels and engineering overview, we are going to discuss about the fuel classes, key properties of the fuel such as calorific value, volatility and viscosity, autoignition property, emission index and cold flow, chemical reactivity properties, and combustion fundamentals and engine fuel matching applications and design thinking approach. The fuels basically classified into two types. One is primary or natural fuels and secondary or artificial fuels. In the primary or natural fuels, further classified into three types: solid fuel, liquid fuel, gaseous fuel. Wood and coal are the best example of solid fuel, and petroleum oil are best example of liquid fuels, and natural gas is the example of gaseous fuel. The secondary or artificial fuels are also classified further into three types: solid fuel, liquid fuel and gaseous fuel. Some of the examples are coal and charcoal is the best example of solid fuels, and diesel and kerosene are the examples of liquid fuel, and coal gas and water gas are the examples of gaseous fuel. So fuels are the energy dense substance that releases the thermal energy through the combustions or chemical reactions. In mechanical engineering, understanding the fuel characteristics is an essential part for optimizing the engine performance, efficiency and the environmental impact. Some of the key parameters to be considered are energy density, combustion efficiency of fuel, and emissions profile, and storage requirement and cost effectiveness. These are the key parameters used to determine the fuel suitability for the specific applications. So these are the primary fuel classifications: fossil fuels, biofuels, alternative fuels. Petroleum based fuels including the petrol, diesel and natural gases are comes under the fossil fuels. It has the high energy density around 42 to 46 megajoule per kilogram, but it releases the significant CO2 emissions. Likewise, renewable alternatives from the biomass like bioethanol, biodiesel, biogas are the examples of the biofuels. It has a lower carbon footprint but reduced energy density compared than the fossil fuels. The ranges between the 26 to 38 megajoule per kilogram. And hydrogen, electricity and synthetic fuels are the examples of alternative fuels. It releases the zero emission potential with evolving the infrastructure requirements. So these are the some of the characteristics and performance of fuels like petrol, diesel, natural gas and liquefied petroleum gas. The petrol or gasoline in the octane rating range between the 87 to 98, it is ideal for the spark ignition engines and volatile at the ambient temperatures. Comes to the diesel engine, the cetane number rating from 40 to 55, the compression ignition engines, it 50% more energy dense than the petrol engines. And natural gas, it is a methane rich gas, cleaner combustion and lower particulate emissions. It requires the pressurized storage arrangements. Liquefied petroleum gas are the propane and butane mix, portable for fuel source and widely used in the heating and transport applications. So first and second generation biofuels are bioethanol, biodiesel, biogas. The bioethanol is fermented from the sugarcane, maize or cellulose biomass, and biodiesel is transerification of vegetable oils and animal fat. This is arrived from the transerification of vegetable oils or the animal fats. And biogas is the anaerobic digestion production methane rich gas. So some of the challenges includes land use competition, water requirements and the feedstock sustainability. These are the some challenges of first and second generation biofuels which are incorporated with the sustainable engineering solutions. So this is a comparative fuel performance analysis of hydrogen, diesel, petrol, biodiesel and the bioethanol and the natural gas usage. So design thinking approach, the first stage of design thinking is the empathize to understanding the need of fuel selection of end user. So some of the challenges are range anxiety with the alternative fuels, refueling the infrastructure availability and operating cost consideration, reliability and the maintenance requirements, and some of the environmental stakeholders are emissions released from the engines such as carbon dioxide, NOx emission, renewable energy integration and life cycle environmental impact and regular The next stages of design thinking stage is prototype. So in the hybrid fuel system development, prototyping dual fuel engines allows to engineers to test the flexible fuel strategies and optimizing the combustion characteristics across the multiple fuel types. So some of the rapid iteration approaches are design fuel injection mapping, and build the test bench prototypes and measure the emissions rate and the efficiency of the engine system and refine the control algorithms. These are some rapid iteration approaches of these fuel types. So some of the real world applications across the sectors are automotive transport, aviation industries and the power generation. In the automotive transport, hybrid petrol electric systems and hydrogen fuel cells and the biodiesel blends transforming the passengers and the commercial vehicles. In the aviation industry, the sustainable aviation fuels SAF reducing the life cycle emissions by up to 80% compared to the conventional jet fuels, and natural gas turbines and biogas cogeneration providing the flexible and dispatchable energy for grid stability. Some of the key takeaways of the fuel engineering: fuel diversity is essential. Design thinking, it drives the innovation and the emissions and the efficiency balance. Future mechanical engineers must prioritize both the thermodynamics performance as well as the environmental responsibility in the fuel selections. So thank you for watching.